and I will talk about complex connection design according to the Eurocode rules. My name is József Szalai. I'm the Technical Director of Consteel Solutions. I will make this presentation now. Just for some practical information, you can hide the control if it is too large, and use the chat options here if you have any message from me. And the content will be first about just basics about csJoint software. Then I will review the connection types, what we can calculate and design. I show how to create a complex joint model, including several different connection types, how to design them, how to modify them, manipulate them, and how to document the results. And then I will show you in Consteel how the structure connection interaction works, and I will show you how can we export model including connections to Tekla structures. So let me start csJoint. What we see here is the introduction screen. We can make new model or we can open model. These are the previous model what can be chosen. Now I choose previous model called joint types, and on this model I would like to show you the different possibilities in csJoint. These are the basic functions. First, to create new joints. The second is we can see the details of a selected joint configuration. We can copy the joint, we can delete, we can document, and we can set default settings. Let me show you connection types. Basically, there are two basic objects in csJoint. The joint is a larger entity which can have several different connections. Now it is a beam to column joint in which on the flange we have a moment end plate connection, and on the web on both sides we have simple plate connections. So it is working as one joint. Sorry, but I hear some voice, so I have to unmute. Okay. So these are the beam to column joints. This is a hinged frame corner joint. This is bracing connections on the web of a column with different bracing elements like angle sections or hollow sections. Fin plate connection on a column, flange or web. This is also a bracing connection and a moment end plate beam connection. This is very typical in industrial, heavy industry buildings, and a simple shear connection. Then we have beam splice joints with same connection types, with the moment connection and splice plate connections. We can have beam to beam joints. This is the fin plate in both sides with different shapes, or can be simple plate, shear plate connections, or moment end plate connections with stiffeners. And we have several bracing types, connections placed on usually on a gusset plate, including these splice plate connections for hollow sections, or with tension bars, I bars. So these are some bracing possibilities. Then we can have column-based joints. This is the moment base plate joint. This is rigid base plate or pinned base plate joint. And we have hollow section joint for truss structures. The chords can be eye-shaped or hollow sections or tube sections, and K, N, T or Y possibilities we have according to the Euro codes. It is automatically evaluated, and it can be a multiplanar truss joint as well. So in 2 planes, and it can rectangular or tube sections. So these are the basic possibilities. Now I show you how to create a joint and how to collect several connections on the same joint. So I click on the create button. I have to give a name. We can choose the settings for the joint, what can be previously modified or created. And in the next button we have to choose the basic joint type. These are the basic types what I showed you earlier. So now we choose the beam to column joint. Next stage is defining the connection types on the column. You can see that we can define 4 connections on both flanges and on both sides of the web. So let me do first and moment end plate connection on the right flange. We can choose a section for it. Let me choose IP 400 for the beam. Okay, we can set here also the column section. That's AG 340. On the left flange we can choose from these types of connection. Let me choose this fin plate with another cross-section type. It is IP 300. And on the web let me choose bracing connections like this with the hollow sections on one side. Okay, and on the other side again bracing on gusset plate. On the middle let me choose the same. This can be compression posts, and maybe I set the lower edge round bar, so tension bar. Okay, so now I created the joint configuration and I push the create button, and we can see now the whole joint what we previously selected for cross sections and for connection types. So this is the moment end plate connection. This is the gusset plate connection with the compression post and the tension bar. This is the fin plate beam connection, and this is the other compression post connection. And now I can start to manipulate the joint. All this, the plates, the bolts, the weds are coming from the default settings, what can be previously set by the user, or using the default arrangement. We should modify it accordingly. So let me make an intermediate story here. And first we can set the joint loading. We can input loading as a new one. We can set several load cases. If we have more, if we don't have a relevant load case, we can set more, and always the dominant relevant one which will be governing for the design. And here we can see all the connection details, connection components for which we have to define loads. So the left flange is the fin plate connection, which can have only shear. All the others are forbidden. Only the shear can be defined here. The second is the right one. Here we can define normal force, shear force, and bending moment as well. So this is a moment and plate connection. Web front, middle. This can be a compression post, so a negative value means that it has a compression. Then on the tension bar, some tension. Here again on the compression. And we can define load on the column as well. Something. So we have now the loads. If we have loads, then automatically every connection is calculated. This is the main window of a csJoint. These are the area where we can choose the connection type which we want to work with and the different components. Here are the parameters of the components, so the geometry, the bolt type, material, etc. This is the 3D graphic of our connections and joint, and this is the area for the results. So on the results area, we can choose these options: summary of the results of the whole joints, including all the connections. It starts with the checks. There are warnings and errors. Errors means that there are something serious mistake, which means that the connection cannot be calculated, cannot be evaluated. Now we don't have such errors. We have only warnings. Now it warns us that the gusset plate buckling is not checked here and here. And then we can see the summary of the results for all the connections. On the right flange, we have this moment and plate connection. We can see all the calculated values in the summary, and what we can see that the moment resistance is not adequate, the utilization is very, very high, and also the weld utilization is high. We will improve it later. On the left flange, we have a fin plate connection. We have only shear resistance. This is the dominant components, the bolts in shear. It is also not adequate at the moment with this default arrangement of bolts and plates. Then web front middle edge. This is here. On the middle edge we have this compression post. We have these summary of the results. On the lower edge we have the tension bar connection, and we have the web back connection. So these are the summary of the results. We can choose the summary of the results only for the selected connection if we want to deal only with one connection. So, for example, first we want to improve the moment end plate connection. Then you can see that we see this right flange connection here. We see all the results for this connection. What are these results? We have two default load cases, a positive loading and a negative loading. It is important for moment connections when the connection is not symmetric. We can see that the moment resistance is not the same for positive and for negative bending moment. But if we have a load case, automatically the relevant resistance is calculated, which is now the positive, and we can see that if we have a load case, then we have utilization values as well. So as I mentioned, the moment utilization is not adequate, shear resistance is adequate, WED calculation is not adequate. We can see here the stiffness as well. The class is semi-rigid. The strength, class of strength is partial strength at the moment. And we can see here the dominant compression and dominant tension components. These are the governing components from the evaluation. So we can see that the weakest component in the compression is the column web in transverse compression at this flange, and the dominant tension components in the highest bolt throw is the column flange in bending. So the bending of this column flange, and the dominant failure mode is the bolt failure, that is the elastic bolt tearing. And we can see here the dominant resistance forces for these tension and compression components. So these are the basic summary of the results. If we want to see the detailed results, we can see here for the dominant load case, which means that it chooses, if we have several load cases, that the one it chooses which produces the highest utilization. We can see the default positive or negative loading, or we can select any load case what we have for see the result. So now we select the dominant, which is of course now the first load case what we have, and we can see the detailed results now. Starting from moment resistance, in every component we can see the relevant chapter of the Eurocode, the relevant section, and these are the compression components, column web panel in shear, column web in transverse compression, and beam flange and web in compression. And we can see the tension components from bolt throw to bolt throw. So for the first bolt throw, we can see the lever arm and the four different component resistance, column web in transfer tension, flange in bending, and plate in bending, beam web in tension. We can see the dominant one and the dominant failure mode. And the same for second bolt throw, we can see individual or bolt throw group 1 and 2, and for all the others. And finally, this is the calculated moment resistance. The axial resistance is calculated here, but it is not relevant now because we don't have axial force at the moment on the connection. We have the shear resistance, the different components, bolts in shear, the bearing resistance of the bolts, and the weld resistance gives the shear resistance. Now the dominant is the bolts in combined shear and tension. And we have separately the weld resistance for web, upper flange and lower flange. These are not adequate. And finally, if we have moment end plate connection, then we can calculate the stiffness of this connection according to the Eurocode chapters. This is also a component-based method, and we can see finally these are the calculated initial stiffness and second stiffness, which is considers the applied moment. And we can see the stiffness class that at the moment it is a semi-rigid connection. So now let me show you how we can improve our connection by utilizing the results. So what we see now that the utilization is very high. So first I would like to make here a hunch on the beam. So we can see we have an IP 400, and with this button we can apply a hunch. We can apply on the top flange or on the bottom flange. Now I choose the bottom flange and hunch with flange, and here we could set the geometry of this hunch. This is the thickness of the web. We choose the same as for the beam, so it is 8 millimeter. Then we can see the height of the hunch, we define it, length of the hunch, thickness of the flange, similar, and width of the flange, it is 180. And we apply this. Okay, so the hunch is taken here. What we see that we have now errors, so the connection cannot be calculated, of course, because the basic error that lower end plane extension is not enough for the hunch flange weld, and for the whole hunch it is not enough. So we have to enlarge, of course, the end plate. It can be done quickly by an update function. This update always tries to improve our connection to be able to calculate it. So the update function now gives a bigger end plate and one more bolt somewhere in this region to have for the hunch. And now we can calculate this connection again. What we can see that it is still not adequate, but the utilization is half, of course, because we have a much larger connection here. The stiffness class is still semi-rigid, and we see now that it is, of course, more stiff. So how to strengthen now to make a fully adequate connection? Let me start to analyze the dominant components. So the weakest part for compression is the column web in transverse compression. It is important because this compression component can reduce the forces on the tension components, on the bolt throws. Okay, and now it is 450 kilonewton, and we can see that in the bolt throw 4 there is no tension, and even in the third bolt throw it is reduced by the column web. So this value is a reduced value because of the compression components. So this is important to keep in mind, that we should strengthen the compression components if we want to strengthen dominantly our connection. Let me see the tension components. It is column flange in bending. Usually if the column flange is the governing, we can strengthen the column flange by adding special stiffeners on the column flange, stiffener or supplementary flange plate. But we can also use another bolt throw, or what we can see here, that the dominant failure mode is bolt failure. That means that the bolt is the weakest component. This is elastic failure. So if we choose a higher material grade for the bolt here, let's see, it's 8.8, then it's better, the situation, and now we can see that now the end plate in bending is the dominant one. So we can increase the thickness of the end plate here, And at 20 we can see that again bolt throw failure and column flange bending, but now it is 150. So let me again modify the bolt to 10.9. Okay, and maybe I take here another bolt throw, and what we can see now that only the first two bolt throws are in tension. The third, fourth and fifth bolt throw, so these ones have no tension because the reduction from the component compression component, it is because of the equilibrium of the compression and tension forces. So now if we want to increase the resistance of our connection, we have to increase the dominant compression component, which is now the column web in transfer compression here. What we can do here is apply a stiffener between the flanges. So stiffeners, we can use upper or lower transverse plate. Here is the stiffener. If we choose to take here the bottom, we have to assign the stiffener to the hunch flange. Now it's there, and we can see it's better the situation, and now the dominant compression component is the column web panel in shear, and still now I have something tension in bolt throw 3, but still reduced by the column web panel in shear. So we have to somehow increase the shear resistance of this web panel, so we can choose the shear stiffeners. There are several shear stiffeners here which can be chosen. Maybe we choose this supplementary web plate, and now we can see that our connection is almost adequate. We can maybe arrange something about the bolts, and now it's fully adequate. So these are the basic functionalities for a moment end plate connection. We can use stiffeners on the column, web stiffeners, flange stiffeners or shear stiffeners. We can use hunch on the beams. We can manipulate here the end plate, the bolts and the bolt distribution, bolt spacing here, and we can make our connection adequate. What is still not good is the weld utilization, which is very high. Let's go to the welds here. What we see here is the different weld sizes. This is now the default. This is the minimum weld size. This can be set by the user to add other value for the flange or web, but now it is taken as the minimum one. The weld design can be based on the section resistance. That means that the weld should resist the whole resistance of the section. It is not really, this is quite a conservative method, especially if we have a partial strength connection, which means that the connection resistance is lower than the cross-section resistance. Then of course the welds shouldn't be the same as the cross-section resistance, but anyway we can choose this, and of course there we can get another utilization. We can choose the design load, which is now the this load, what is applied on our connection, or the weakest component. What does it mean, weakest component? The weakest component means that, for example, this upper flange welds should resist only this tension force coming from this area, from the first two bolt throws, because this is a plastic force distribution, and not higher forces taken to this web, only this. If we have an extended end plate, of course these two two bolts resistance should be resisted by the flange wedge. The web wedge should resist the shear, and the lower wedge should resist the compression components. Now we choose the design load. So we have now shear force and bending moment, and we evaluate the wedge according to this. We have three options here. So we can increase manually here the sizes of the wedge, but we have three options. We can make the throat thickness as half of the plate thickness. We can choose automatic wedge optimization, and we can choose that linear stress distribution is considered on the web wedge for bending resistance. That means this is a very good option if we want to reduce the wedge size, that we consider that the web wedges are not fully utilized by the shear. So the web wedge has more resistance to consider linear stress distribution for the moment. So that means that the web wedge can resist some moment, and it will reduce the moment which is taken to the flange wedge. So now we choose this option. Then we can see that the utilization is with the same sizes is much lower. Here we can see the details. In this case, the web wedge utilization is near 100, but still not enough for the moment and the flange wedge. Now we can choose the automatic wedge optimization using this option, and now we can see that the automatic wedge optimization gave 4 millimeters for the upper flange wedge and 5 millimeters for the lower hunch wedge. But at the moment, it is there is some error. The upper end plate extension is not enough for the beam flange wedge. We can see here that this weld is larger, so we have to improve our connection again. We use again this update function, and now we can see that everything is adequate. So the bending moment utilization, the shear utilization, wedge utilization is good, no error, and we can see here the detailed results. So these are the basic functionalities. How can we solve moment and plate connection within a joint? So let me go on the connection and see now the fin plate connection. This is the detailed results for the fin plate connection. Of course, it is much the results are shorter because this is just a shear connection, but we can see that it is not adequate. We can see the dominant component. Dominant components are the bolts in shear. So maybe we have to apply more bolts in this fin plate. So we go to the fin plate and we increase here the number of bolt rows to 3, and the distances we want to even a little bit. It's 80 between. Okay, and we can decrease the height a little bit, and now it's adequate now with 3 bolt rows. So in shear resistance for fin plate, the bolts in shear, the bearing resistance, the shear resistance of the fin plate, the wedge resistance, shear resistance of the beam is checked. And now instead of the bolts, the dominant component is the shear resistance of the beam web, but it is adequate at the moment. Okay, this was the fin plate. Now we can go on to the gusset plate connections. So in this gusset plate connection, we have two different connections, hollow section connection with a compression post and a tension bar connection. What we can see that the hollow section connection is adequate. Here we can see all the details. What we see that the dominant component is the shear resistance of the boards, where it is acceptable maybe this utilization. What is quite low is the weld utilization. The weld, maybe the weld is too long, so we can go to the splice plate side here and we can shorten the weld size. We can see here now the weld is too short, so it is under the minimum, so we have to increase back, and now it's good. This is the minimum weld side, but it is a higher utilization, but still good, of course. And this is now the default arrangement. We can define here other values to make it with different geometry. It's, yes. And we can see again this is not appropriate. Yeah. Web weld is too short. Plate is. Yeah, this is. Yeah. So we can manipulate here the connection and the boards as well. Now we use M12 boards with this board grid, but it is adequate for this. So let me show you the lower edge splice plate connection. This is a tension bar. We can see the default arrangement. The utilization is quite low. We can change here. These are the possible configuration for all splice plate connections, even for this this type of hollow section. So we can choose this one with 2 plates, or this one. So there are 4 configuration types, and it is same for each splice plate connection here as well. So we can choose this. There are 4 different configurations. Now we stay on this and see again. Maybe we can use here only one bolt column. So we reduce the number of columns to 1. And we can reduce also the weld length. We can see that the utilization for the weld is also quite low. So maybe we can apply the minimum value again. Okay, and now it's good. It is very important that in case of gusset plate connection, the gusset plate is always automatically optimized. We can set here basic settings for the gusset plates, but the position, some geometry for these distances, and if we change something on the connection, the gusset plate is automatically refreshed with geometry. For example, if the angle of the brace is different, and we can see that the gusset plate is larger and larger to make it good. So it is always automatically optimized because all the braces should have the same point. Okay, we can see. So these are the basic manipulations with the connections. This is quite the same as the earlier one. So now let me show you the documentation and how it looks. So we push now the document here, making a new document. These are what can be documented, table of loads, and all the connections. Now we have 5 different connections on the left flange, on the right flange, and web front 2 connections and web back 1 connection. For each connection we have a joint, geometry, we have results. For each load cases now we choose only the dominant case, and these are the detailed results for the dominant load case, or we can choose only the summary. We now see the detailed results and create the documentation. This is the basic document, this is the tables. We can switch here. So this is the first page with the title, model, standard. This is the contents, table of loads, and now we can see from connection to connection all the results, starting from the joint geometry and the connection geometry inside the joint, the load case which is dominant for this connection if we have more load cases, and then the detailed results. And it is the same for the moment and plate connection. Of course, here we have larger results. This is the web front. This is the tension bar. And finally the web back connection. So this is the documentation for the connection. Okay, and what we have left is to show you the structure, connection, interaction within the Consti software. So this was about the csJoint software, which is a module of Consti, but we sell it separately as well. And now I show how it works inside Consti. So I open a model, I prepare the hole with the podium, and we have load cases, load combination, we have analysis results, we have lots of things, and we have several joints placed to this structure. What I would like to show you how it works, this interaction. So maybe I want to create a joint, a complex joint here. Then I can use the create joint by model functionality, in which I have to pick up the node where I would like to place a joint. I pick up this node, and then it is identified. In this node we have a column, we have a beam, and we have 3 other bracing elements. We can choose these types of connections here. We choose now this one. The next stage, it is automatically identified that on the column we have 1 connection on 1 flange and 2 connections on both sides of the web. So we have to now define the connection types. So for the flange we select this one. This is, we can see that this is the hinged beam, so maybe moment and plate connection would be appropriate. And for the Gusset plate connection we can choose these ones. For the other we have only one here. And then we create the connection. We have here, what is very important, that everything is coming from the global model. So the angle of the beam, the column cross-section, beam cross-section, the geometry of the hinge, and the angle of this bracing connection, the other cross sections of this bracing are coming from the model, and then the same is applied as I showed you in constant joint. With the default arrangement, we get these values. The next stage is that we have this and we have to check this connection to the loads what we earned from the global calculation. So we push this place button. We place back this configuration to the global model. So we push here and we have a new joint here, including several connections, as we see. So 4 different connections in one joint. And now with end joint placement, we finish it. We can place this joint, if we have the same configuration, to several positions in our global model. And now we can see the results. What we can see that the loads are automatically imported from the model. We have now calculated 3 combinations. We can see here. Okay. We can see here the combination results with the appropriate bending moments and internal forces, and all these results are coming to here, and the dominant one is picked up for each connection and it is evaluated for them. We can see that it is slightly not adequate, and we can just quickly improve it. Maybe first I take it down a little bit. Okay, then some quick manipulation to have a real joint. Okay, maybe apply 2 stiffeners here, and maybe quickly apply. Okay, now it's adequate, only the welds are wrong. Maybe the linear stress distribution, yeah. Now everything is good in our connection. So I quickly repaired it. We can see here all the details, and now we have a ready connection. And what I would like to show, I save this. Okay, now it is placed back to here, and in the analysis we can evaluate again the model, and the joint stiffness is automatically accounted for in the global analysis, and it is taken into account not only in the first order calculation but in the backlink calculation as well. And one more topic is that if we have placed connections, like we have in this model lots of placed connections, then we can use special export to Tekla structures and even to StruCAD. I will show you how it works. Now we have opened an empty model in Tekla, and I would like to now export the whole model, including all the placed connections, to Tekla. I choose the export to Tekla structures. I have to select the objects. I select all of them, pick a reference point, which can be this point, and push the export. There are the names. Maybe for Tekla I have to change the name of this run bar, but all the other names are automatically identified. Okay, and then pick the reference point in Tekla structures. So then I go to Tekla, pick a point, and then we can see that the whole model is first with the elements are exported, and then all the joints, all the connections are exported. I now look for the connection. This is the connection what we identified and created now with this end plate connection, with the compression post connection and the tension bar connection. We can see that all the connection components are automatically taken to Tekla, filling the appropriate Tekla macro with all the weld sizes and all the bolts, the grades, the plates, and everything in the right place. So if we use an accurate model in our calculation software in Consteel and define the correctly designed and checked connection, then the whole connection can be automatically, and the whole model including the connections can be automatically taken to Tekla, and these connections are now already checked. So this was the webinar. If you have any question now, I unmute maybe all of you, unmute all. If you have questions, then we have time to answer it. Okay. Then if no question, then we finish this webinar. Thank you for your participation, and I hope it was useful, and maybe I show you our web page. On our web page you may find lots of additional information, including videos, manuals, and lots of information about Consteel and csJoint software. You may download a tryout version with full functionality, and you can try out. So thank you for participation. Bye.